Good morning, wonderful, amazing, fantastic geometry students. This is Miss Youngblood here, bringing you the review topic for Wednesday, March 25th, which is similarity transformations, primarily focusing on dilations. So I'm going to start by reviewing two of the problems on the handout that was given and is posted on Google Classroom. Keep in mind I only go 6 problems because the answers to the 6 problems on the back of the paper. So start by looking at the handout for today. Looking at number 1, our scale factor k is given to us. It is 2. So what we're going to do with that scale factor is multiply each coordinate of each point by 2. Because our scale factor is 2, you can see that our figure is enlarged. It gets bigger. That's because our scale factor is greater than 1. So the first point we're looking at is this point here, -1, 2, which is e. We're going to multiply the x and y by 2. -1 times 2 is -2. 2 times 2 is 4. So our new e, or e prime, is going to be -2, +4. Then we looked at f. F is 2, 0. Again, multiplying by 2. 2 times 2 is 4. 0 times 2 is 0. So our new f, or f prime, is 4, 0. Last point is d, 0, -2. Again, we're multiplying this point by the scale factor k. 0 times 2 is 0. -2 times 2 is -4. So our new d, or d prime, is 0, -4. I connected those 3 dots, or those 3 points, to get us the enlarged figure of triangle DEF. Jumping down to problem 5, we're given a fraction as our scale factor. We can work with fractions. All you have to do is change them to decimals, or you could multiply by the top number and divide by the bottom number to multiply the fraction. I found it easiest to change mine to a decimal though. So our scale factor, k, is 0.5. 1 divided by 2 is 0.5. So again, we're doing the same thing we did in problem 1, multiplying the x and y coordinates of each point by that scale factor k. Our first point is -1, -2, this point down here, which is d. -1 times 0.5 is -0.5. -2 times 0.5 is -1. So our first point, d, is going to be reduced. It's going to get smaller, again, because our k factor is less than 1. So that means we're going -half, not a full unit, half of a unit, and then down 1. Now we're going to look at the next point, 2, -2, this point down here, f. We're going to multiply by half. So 2 times half is 1. -2 times half is -1. So this point f is going to reduce to this new point f prime, which is 1, -1. Our last point, our last point is -2, +2, e. So again, we're going to multiply by 0.5. -2 times 0.5 is -1. 2 times 0.5 is 1. So that point e reduces to our new point e, e prime, which is -1, 1. Now let's take a look at the Khan Academy problem set that was assigned for this review topic. It's a little more challenging because they want you to think conceptually about what words like similar, congruent, dilations, what those words are actually doing to the figures. So the first problem in my set, I was given this problem. It says Bastian was able to map quadrilateral OPQR onto ONML using a reflection and dilation. So this was his original quadrilateral 4-sided shape. It says he reflected it and then he dilated it. So this is our final shape. Original shape was OPQR. New shape was ONML. It says that Bastian concluded, I was able to map quadrilateral OPQR onto quadrilateral ONML using a sequence of rigid transformations and dilations. So the figures are similar. So rigid transformations are transformations that don't change the size of a shape. The shape's going to be the same regardless, but if it's rigid, you're just shifting it. You're shifting it. We learned about 3 rigid transformations, also called isometries: shifts, flips, and turns. Those three isometries or rigid transformations don't change the size of a particular figure. The figure looks exactly the same, it's just in a different position. And now he's saying that the figures are similar. So again, congruent means they're exactly the same. If we would have just done a rigid transformation, such as the reflection he did here, they would be exactly the same, so they would be congruent. However, because of the dilation, the size has now changed. So they are similar. They look almost the same, but not quite, because their size is different. So it asks us to try to just figure out what error Bastian made in his conclusion. So it says the first option is Bastian used a reflection, so the quadrilaterals aren't similar. Again, you can use a reflection and have similar figures. Similar just means they look the same, they just have different sizes. Second option, Bastian used a dilation, so the figures aren't similar. Again, a dilation still produces similar figures because the shape is the same, the size is just different. So the correct answer for this one should be C. The next problem states, a rectangle is, and we have to choose, sometimes, always, never, similar to another rectangle because we can sometimes, always, and never map one onto the other using only dilations and rigid transformations. Ooh, this one's going to be a tricky one. So let's think about rectangles. Rectangles, what do all rectangles have in common? Let me put on my do not disturb. So, as I was saying, you know, all rectangles have 4 right angles. So if all their angles are the same, that means that they're all going to be similar. I don't know how else to describe that. If you have questions on that, please ask me down below so I can elaborate if necessary. So all rectangles are going to be similar. If you wanted to map one rectangle onto another, all you would have to do is either shift, flip, or turn it, and then either make it bigger or smaller, and you could literally make the same rectangle. Might be a messy process, but you can always map a rectangle onto another rectangle. So let's figure out what these answers should be. A rectangle is always similar to another rectangle because we can always map one onto the other using only dilations and rigid transformations. Happen to be incorrect. Let's think about that a little bit differently. My apologies for that mistake. We all make mistakes. We're all human. So I have to reflect on this problem a little bit more deeply. I think when I was initially thinking of it, I was only thinking of triangles, and I was thinking of the angle-angle similarity theorem, but that only works for triangles. If we have rectangles, we actually have a little bit more flexibility. So let's look at a counterexample that shows why that is not always true. So we have, if we're given this rectangle, a random rectangle, 2 by 5, and we are asked to find a similar rectangle. Again, we could shift it any way we want to. Let's say we were shifting to this rectangle here. We would shift it to the right and down, and it would be in the same position, and then we would blow it up and dilate it. Keep in mind when you're doing dilations, you have to be using the same scale factor for all sides. So that means we could multiply these sides by 2, we would get 4 and 10. So this would be a similar figure, a similar rectangle to this rectangle. However, that's not the only option for a rectangle. Every rectangle with a side length of 4 doesn't necessarily have to have another side length of 10. Here's another example. If we were trying to show that these two rectangles are similar, again, we could shift it down, translate it down, so it would be in the same position, and then dilate it. So we see to go from 2 to 4, we'd multiply by 2. However, when we multiply 5 by 2, we don't get 7. So these two rectangles aren't similar. So there are some times when rectangles will be similar and sometimes when they will not be similar. So that's why both answers for that one were sometimes. Okay, so in this particular problem, in the problem set, we're given 2 circles And Pedro is trying to determine whether or not circles A and B are similar by using rigid transformations and dilations. So as you can see, he translated circle A so that the centers matched up with circle B. So he went up 4, left 4 to translate A to the same position as B. And from here, Pedro attempted to say that we cannot say they are similar because the dashed circle does not match up with the inner circle. However, given the options, there was more work Pedro could have done. So if Pedro would have dilated the circle from A to B, then the circles would be similar because he's showing that they can be mapped from one to the other by using a rigid transformation. In this case was a translation, and a dilation, which in this case would be a reduction because he's trying to make the circle smaller from this dashed circle to the smaller circle. So again, that's why B would be the correct answer for this one. So this last problem is actually very challenging. We're given a quadrilateral L, M, N, R, and we're asked to see if we can map it on to P, Q, N, O. In order to do that, the first thing that the example tries to do is rotate it. So they're rotating it around this point N. So M is rotated 180 degrees. L is rotated 180 degrees. And R is rotated 180 degrees. So this little dashed figure here is the rotated version. So that's what it looks like when it's rotated. And then they're attempting to dilate it again about this point N. To do that, looked at how far this point was from this point N. So we would go, I believe it's, let's zoom in a little bit. Up 3, right 2. From that point to double it, they went again. Up 3, right 2. So that point maps there. This point is a distance of 4, so they doubled that distance of 4. So that's that point right there. Again, this point here was a distance of down 1, left 2. Is that left? Right, sorry. Down 1, right 2. So again, they doubled that distance, down 1, right 2. So we can see these other points mapped well by multiplying by 2, but this point did not map to this new point by multiplying by 2. Therefore, the dilation applied to this original figure did not map to this in-between figure, did not map to the new figure P, Q, N, O. So again, because the rotation and dilation did not map very accurately to this new figure, that's why these two figures are not going to be similar. So again, for this one, the answer would be, this is correct because they are not similar. One problem that we haven't really talked about, or one answer possibility that we haven't really talked about, I believe is the first one. Yeah, so it says one more transformation, a vertical stretch, would map quadrilateral L, M, N, R to P, Q, N, O. A vertical stretch is transformation that is used on functions really, not really on figures in the coordinate plane, at least not that I've seen in high school geometry. But a vertical stretch is only going to stretch a figure vertically, so it's not a dilation because it's not producing a similar figure. If you're just stretching it vertically, you're not changing all of the side lengths proportionally, so it's not going to be a dilation. Again, not something we get too much into detail with, but a good problem to kind of work your brain. So that concludes our review of similarity transformations and dilations for geometry. I want to close off by looking at the daily meditation for yesterday, which would have been the 24th. The daily meditation for yesterday, the question was, how do you respond when someone sends negative energy in your direction? My response was, I never experienced an abundance of bullying when I was younger, but there were definitely times when I felt like people would try me. I used to believe that ignoring them was the best option, but I slowly began to realize that didn't work for me. Ignoring ignorant comments would frequently cause me to internalize those comments and develop low self-esteem. I would also occasionally have random situations where I would go off on people unnecessarily because I had so much pent-up frustration toward them. As I've matured, I've recognized the importance of speaking up as much as possible when something is said or done that bothers me. I definitely choose my battles and recognize that this isn't always the best option for everyone. However, I believe that speaking up releases some of the negative energy that was initially cast in your direction. And my song of the day for yesterday was Be Alright by Evan and Eris. Again, if you want to share your thoughts on a daily meditation or your song of the day that you've been listening to try to get through these stressful times, you can comment that down below on YouTube, on Google Classroom, or you can message me privately through email or text if you want to share that information. Also, if you need help with your specific Khan Academy problems, or if you need help with the handout that was given or posted on Google Classroom, again, reach out to me if you need that assistance. I'm here if you need me. I thank you so much for taking the time to watch this video, and I will see you soon.